Hello, my name is Avi Kantha, and today I'll be discussing my lab 5, the falling slinky in PHYS 2211. For some introduction, this lab aims to show the observer's expected motion of a stretched out slinky and see whether they fall the same way. The object will be observed is slinky, the observed motion will be seen using tracker, and the predicted motion will be seen using glow script. The lab will understand tension, drag in detail, as well as Newton's second law. The system is slinky, the surroundings of the Earth. For Newton's second law, we need to know a little bit about it, so we use the important equation F equals ma, which comes from Newton's second law. However, this equation can be manipulated by changing acceleration to delta v over delta t. We can manipulate the equation to become velocity final is equal to velocity initial plus f net over m times delta t, known as the velocity update formula. We also need to know the position update formula, which is final position is equal to initial position plus average velocity times the change in time. For the purpose of lab, we also need to use the formula of drag, which is given right here. This is a little preview for our results. So our observed position using tracker, so what we did is we inserted our video, then set the video length. We inserted our axes using the coordinate plane. We put the 0, 0 at the bottom of the slinky. We inserted our calibration stick by using Derek's height, which is 1.75 meters. And then we plotted points at different intervals of the falling slinky, and then observed the table and graph. Through our tracker findings, we found that the mass, found the initial position, initial velocity, and the mass of the slinky we found using the average mass of the slinky. All these findings were necessary to create a glow script model. So then we plugged in our mass and our position and velocity. We put in our initial time and our change in time. We plugged in our gravitational constant, our j hat, which is just the y direction, positive y direction vector, and our b, which we just did through trial and error. I just decided to stick with 75 for our drag constant. So for our first while loop, what we had to do was look at the constant, the time in which the bottom of the slinky wasn't moving, and this time was before 0.353 that I found from my table earlier. And over here we have a tension force, and the tension force is negated through the weight. Therefore we have F net of 0, meaning it will not move during the time that there is a tension, because the bottom of the spring is acting as a spring. We plug in our velocity update and position update formula in order to find that. And we do that here again, where we plug in our the exact same thing, where we plug in our ball velocity and ball position. However, now what we don't have is a tension, but now we have a drag force, because the tension is gone now, because the slinky's together, and now it's just acting as a point mass. So now we just look at the weight and the drag force, and we add them together to find our F net. This time the F net will not be negative, or it will not be 0, but we will have an F net, meaning that the bottom slinky is not moving. And then we put our observed position versus our predicted position together. So our predicted position is seen using orange, and the observed position is seen using green. You can see that it does stay 0 it does stay stationary in both models. However, in our predicted motion, it goes a lot slower, or it doesn't move as much as the observed position is. And some possible reasons for errors like that could be outside forces, such as like air resistance. Slight errors in measurements, like measurement taken in the video, can be inaccurate. Point plotting, some of the points are not in place completely accurately. And inaccurate glow script code, where some error must be presented in the code, giving a graph a completely different value compared to observed value. So what does it mean? So does the bottom slinky stay stationary like in the video? So yeah, it does. But why does it stay stationary? It stays stationary because it is acting like a spring. Therefore, there is a tension force. The tension force is exactly negative to the gravitational force, as we're looking at only this positive y direction. Hence, the F net is 0, meaning that there's no velocity, meaning that the bottom will stay stationary for the duration, acts as a spring. So what if the gravity was less than Earth? Was this more? Would the bottom still stay stationary? It does not matter whether gravity was less or more, because the tension force will always be negative Fg, in the case that we're looking at we're dropping slinky at only the positive y direction. If there's more gravity, there'll be more tension. If there's less gravity, there'll be less tension. Hence, the bottom will stay stationary regardless. Thank you for listening to my presentation.